always, please check us out online, and we'll always have the video up by Friday and lecture slides online also. And feel free to add yourself to our seminar mailing list. And thank you very much.
So good afternoon, everybody. My name is Khun Nguyen, and I'm host this seminar. And it's my great pleasure to introduce Professor Tim Kelly. He received his bachelor degree in science in chemistry from Memorial University in 2005. And then he moved to the West Coast to pursue a PhD under the supervision of Professor Michael Wolff at the University of British Columbia. And from 2009 to 2011, he actually spent time at the University of California, San Diego, where he spent the postdoc working with Professor Michael Saylor. And since July 2011, he has been an assistant professor at the University of Saskatchewan, and he actually holds a Tier 2 Canada research chair in photovoltaic. It's great to have him here, and we can learn something about perovskite solar cell. So please join me to welcome Professor Tim Kelly.
All right, well, thanks, Quinn. And thanks very much for the invitation to come here and get out of the cold, give a talk in sunny Southern California. And it's been a great day of science, great day of meetings, catching up with old friends and meeting some new ones. So because Saskatchewan is probably not the first place you think of when you think of Canada, I thought I would just take a minute and point out where we are on the map. So this is our campus. We're located in the Canadian Midwest. If you want to think of us as Montana North, that would be about right. But we're as the largest school in the province. We're a fairly sizable institution, about 20,000 students. A member of this U15, which is some of the more research-intensive Canadian schools. And most importantly for this talk, we're also home to the Canadian Light Source. So that's Canada's national synchrotron facility, which is about 10 minutes walk from the front door of my lab. So it's very, very convenient to have that exceptional resources, many of you know, so close nearby. So I started work at the U of S about 3 or 4 years ago. And our group was largely focused around developing emerging photovoltaic technologies, things a number of you work on yourselves, OPVs, organic photovoltaics, dye-sensitized solar cells, and most recently perovskites. And to try to improve efficiencies or longevities, we've employed a pretty diverse toolkit. We've looked at everything from metal nanoparticles and plasmonic enhancements, through to what's now a fairly robust synthetic organic program, the synthesis of new organic semiconductors and polymers, and even some collaborative work on two-photon upconversion and triplet-triplet annihilation. But probably what we're, at this point, best well known for are these things, our perovskite solar cells, and so that's what I'm going to be telling you about today. So just a little reminder, I'm not going to belabor the point, particularly to an audience like this one, but it's worth reminding ourselves why we're interested in alternatives to silicon. Of course, it's one of the most dominant technologies out there. We have a small solar array on our U of S campus of multicrystalline silicon panels. But of course, the problem with silicon is you have to fish it out from silicon dioxide. That's a very energy-intensive process, thermodynamically uphill. And so you have to put an awful lot of energy into making a silicon panel. And so Dale and Benson did a nice meta-analysis in this environmental science and technology paper looking at the energy costs associated with constructing, operating, and decommissioning various technologies. And the long story short is that it takes an awful long time, upwards of years, to get the energy back out of a silicon panel that you put into it. And so this is where emerging technologies like organic photovoltaics, DSSCs, and perovskites really come into play. And so back in 2009, I guess I was finishing up as a graduate student at UBC, is really where the first examples of perovskite solar cells came into play. And it really came out of the dye-sensitized solar cell community. by some very pioneering work by Miyasaka's group out of Japan. And they took this methyl ammonium lead iodide compound, which adopts the perovskite crystal structure, and they took small nanoparticles of this and adhered it to a titanium dioxide surface. And they built a conventional dye-sensitized solar cell. So using an acetonitrile-based electrolyte, the perovskite injects an electron into TiO2, goes around the circuit, is carried back by the redox mediator, and completes the device. Now the devices worked, 3 or 4% efficiency, respectable at the time, but certainly nothing record-setting. But they were very promising. You can see in the IPCE spectrum, they absorb out to about 800. In the case of the bromides, we got very, very nice open circuit voltages. So there was a lot of potential here. But it wasn't until 2012 from work in the Gratzel lab that the field really took off. And so the problem with perovskite is that it was actually dissolving in the acetonitrile electrolyte. And so it's actually kind of amazing that they were even able to get 3 or 4% out of those first devices. But if you switch to a solid-state hole conductor like spirometad, you no longer have that issue. Gratzel was able to prepare devices with efficiencies of about 10%. And that's really where a lot of the community started to sit up and take notice, because now you had something that was competitive with champion ruthenium dyes. So efficiencies of about 10%. And that was about as good as they could do at the time. And so where we started to come into the picture was actually in the summer of 2013. And so I just had a really ambitious postdoc who had just joined the group. He really wanted to work in this field. And we had just seen this really nice paper, again from the Gratzel lab, published in Nature. And what they had done was adapt nice approaches originally developed by David Mitzi to produce crystal perovskite films via this two-step deposition procedure. So what you do is you take a mesoporous titania framework, you spin coat a layer of lead iodide from DMF solution, and then you simply soak that in a solution of methyl ammonium iodide in isopropanol. And what happens is the methyl ammonium iodide salt basically intercalates between the PbI2 sheets and starts forming the perovskite in situ. So they were able to get very nice crystallinities, very nice power conversion efficiencies, and this was far better than any other solution process technology really out there at the time. And so we were really interested in this postdoc in particular in trying to drive this technology forward.
I'm sorry, are you showing the methyl ammonium on your picture? Or what is changing between those two pictures? Are you just forming vertical?
So this is the methyl ammonium cation here. All we're doing is this is intercalating. You're actually condensing to form the perovskite structure where now you have these corner sharing octahedra. So it's really the three-dimensional structure plus the addition of these methyl ammonium cations to the structure.
And are those iodines, do they come on and off? You wrote the I3 single minus before and things like that. Are you exchanging iodine from your crystal?
So we can get to that a little bit later on when I start talking about the stability of these, but not so much. I'll touch on that a little later on. So what we were trying to do was really rationalize this with the work of Henry Snaith from Oxford. And what he had demonstrated about a year earlier was that if you replace the mesoporous titania with mesoporous alumina, not only does the cell still work, it actually can even work a little better. And in the context of a dye-sensitized solar cell, this really makes no sense because the alumina conduction band is sky high. There's no way you're injecting an electron into the alumina framework to get transport to the counter electrode. And so we were really trying to puzzle this out, and we wanted to ask a couple of very simple questions. And so the first was, if the mesoporous scaffold is not absolutely essential for charge transport, if it doesn't have to be there, can we take it out? Can we make a planar device? And at the same time, we knew that, of course, titanium dioxide worked, but zinc oxide, very similar band structure, and zinc oxide nanoparticles have been used quite extensively in the organic photovoltaic literature to make inverted structures. And so we wanted to see if we could replace that compact layer of TiO2 with something based on zinc oxide. And so that's what we set out to do. I always tell my organic colleagues that this is my total synthesis of a natural product. So the synthesis of these zinc oxide nanoparticles is really very straightforward. All you do is take zinc acetate, throw in potassium hydroxide and methanol, forms the zinc oxide, and if you solubilize that appropriately, you have something that you can now spin coat from solution. So you form a nice compact electron transport layer. So that's exactly what we did. So we produced a thin film of zinc oxide on ITO, and then we followed Gratzel's protocols. So spin coating a layer of lead iodide from DMF, soaking that in the methyl ammonium iodide solution, forms the perovskite, and we finished that off with a spiral-omitad whole transport layer and a silver counter-electrode. And the devices actually worked pretty well. They actually worked so well I didn't quite believe my postdoc at first and said, okay, go back and make more devices, more devices. So we had a nice distribution here of about 100 separate cells across multiple substrates. And of course, the kind of sneaky advantage to making 100 devices is you're statistically guaranteed a 3 sigma outlier, and that was our best device out here. And so even though our average is around 13 or 14%, of course, our best device is a little bit above that. So it was quite gratifying to see that we could actually make a high efficiency planar heterojunction. Of course, the problem was we went to write this work up, and almost to the day that we went to submit it, Henry Snaith published this in Nature, which is a planar heterojunction perovskite solar cell on a compact layer of titanium dioxide. So we deposited this by a vapor phase co-deposition approach, very, very similar planar structure. So we were a little bit bummed. But on the other hand, it was actually nice to see that our efficiencies were quite in line with what Snaith was observing at Oxford. It was nice to know that this wasn't a fluke. This was quite reproducible, obviously, across multiple different deposition methods, that you could certainly actually make a planar heterojunction device. But we had one selling point, of course, to our zinc oxide approach, and that was the processing temperatures that are involved. So typically, if you want to put down a compact layer of titanium dioxide, you might do that by spray pyrolysis, elevated temperatures. You might spin coat titanium isopropoxide and sinter it at 450. But either way, you're at a high temperature, and so you can't work on thermally sensitive substrates like plastics. Whereas with the zinc oxide, we spin coat it, we let it air dry, and so there's really no elevated temperatures involved in the processing. And so what we did was we made some flexible devices on polyethylene terephthalate substrates. They worked reasonably well, efficiencies of up to 10%. So certainly a really nice flexible technology. I finally got to take one of these bendy solar cell pictures. I don't know how many of you have already taken one. My PhD, my postdoc was not in this field. So being able to take the glamour shot with the flexible device in my own lab was kind of a nice touchstone for me. So we published the work. The devices seem to work pretty well. And it's worth bearing in mind part of the reason why that is. If you compare them to organic or dye-sensitized designs, the mechanism is a little bit different. The exciton binding energy in these perovskites, it's been variously measured or estimated, but it's kT or less than kT. And so really, these are not excitonic cells in the true sense of the word. You're forming free charge carriers as part of this photon absorption process, meaning you don't have to waste a lot of energy in terms of breaking that exciton. And so if you compare the optical band gap for various DSSC dyes, various polymer systems, and compare that to the VOC that you get, the losses here can be really quite staggering. Whereas in the case of the perovskite devices, it's a much more modest decrease or modest difference between the optical band gap and the open circuit voltage. Of course, the other nice thing is that it's not a long, laborious synthetic process. If you take methylamine and react it with HI, you get methyl ammonium iodide. And this is chemistry that even physicists and electrical engineers can feel pretty comfortable doing. So after some of our initial work, we wanted to try and take a step back and really see how we could optimize some of these systems. And so one of the obvious things to do is, well, okay, well, why don't you simply just try changing the thickness of your perovskite layer? How does the thickness of the film affect the amount of light that you can absorb? And how does it affect your carrier collection? And so we actually had to take a bit of a step back at this point. We couldn't really use solution processing for the lead iodide because we were already working very close to the solubility limit in DMF. It's been very, very difficult to work with these concentrated solutions. And so what we did is we took another page from David Mitzi's playbook, evaporated thin films of lead iodide. Gives us very, very nice control now over the lead iodide thickness. And we can convert that to the perovskite really nicely so that we get an almost linear correlation between the thickness of the perovskite and the thickness of the lead iodide starting film. And there's a little bit of a tail off here at the thicker films. And from PXRD, we know that that's due to a little bit of incomplete conversion. So there's about a twofold expansion of the film simply due to the change in molar volume between the perovskite and lead iodide. And this really reflects just a little bit of unreacted starting material. But of course, Beer's law still holds true. And so we can increase the optical density of our films by increasing the film thickness. And so from the perspective of light harvesting, this is a good thing. You make your film thicker, you absorb more light. In theory, that should give you more electrons. But the counterpoint to that is the carrier collection efficiency. So your electrons only count if they actually make it into the circuit. If they recombine within the film, it simply doesn't matter. And so what we found was that as you increase the perovskite thickness, initially you see a dramatic increase in current, and that's simply a consequence of Beer's law. So you're absorbing more photons, more electrons, more current. But the problem is once you get past this 330 nanometer sweet spot, the efficiency tanks. It plummets because you've really, at this point, exceeded the charge carrier diffusion length. And so the electrons in the holes simply have too far to go before they can reach the electrodes. They're not efficiently extracted from the device, and they recombine. And so your currents start to go down, as does your fill factor. And so we're really, in these films, dancing on the edge of a knife. So if you go too far one way, you're not absorbing enough light. If you go too far the other way, you're not extracting enough of the carriers. And so we actually got very, very lucky in our first time out. With the solution processed films, we were sitting right at about 300 nanometers. Whereas if we had used a little bit more of a dilute solution, our efficiencies wouldn't have been 13 or 14. They would have been more like 9 or 10. I should also point out, as a young assistant professor for this follow-up work, I had switched to the more economical poly-3-hexylthiophene as opposed to the egregiously expensive spirolimetad. So as this was going on, of course, there were lots of groups elsewhere in the world working in this area. It was sort of a real white-knuckle ride in terms of how many competitors were out there. And so we wanted to try and focus a little bit on what we knew we could do well. And so that was make flexible devices. And so there was an interesting question about how flexible these perovskite materials actually were. These are not polymers, which are potentially a little more mechanically robust. These are essentially inorganic crystals. And we're not really sure how flexible they're going to be. We're in a thin film, and that's true. That's working to our advantage. But it's not inherently obvious that these really should be very flexible cells. So what we wanted to do is take our perovskite films, bend them, look at the fatigue resistance, and see how that affects device efficiency. And of course, for anyone who's worked on ITO, this is pretty obvious. But the problem here is that when you start bending your flexible device over many repeated cycles, the first thing to go is not the perovskite film, but it's your ITO electrode. And your ITO simply shatters, cracks into a million pieces, and your device efficiency plummets. And if you, in fact, do this with a perovskite film on top, all of the cracks you see running through are simply due to cracking of the ITO. And so we really wanted to investigate not the flexibility of ITO, that's been done, but how flexible are these perovskite films. And so what we did is we actually switched to a highly conductive PPSS electrode, so something that's inherently a little more mechanically robust. You can bend one of these electrodes through 2,000 cycles. It looks fine, or at least it looks as good as it did when you started. And if you now put a perovskite film on top of this and go through the same bending cycles, so the same fatiguing process, you now start to see the appearance of cracks running through the perovskite film. And we know that those aren't due to the PPSS electrode. Those are actually due to the cracking of the perovskite film itself. And from a mechanical perspective, cracks are bad. And so the question is just how bad are they? So we built some devices. We mechanically fatigued the devices in the same way and compared them to organic photovoltaic analogs. So we built some P3HT PCBM control devices, again on the same PPSS highly conductive electrode. We mechanically fatigued them through 2,000 bending cycles, and you see a decrease in efficiency, which is what you might expect. But in the case of the perovskite devices, that decrease is very much more pronounced. It's a very, very rapid loss of efficiency as you start to form those cracks within the perovskite film. And so compared to organic materials, and for anyone who works on organics, this is really good news, the perovskite really can't compete in applications where repeated mechanical fatigue is likely to be an issue because you're simply going to crack that perovskite film. We did these on 9 separate devices. So these are averages over 9 separate cycles of bending. The student, Kinush, did an awful lot of this in the glove box. I think he was a little tired of it by the end. I think he was happy to get this paper out. But what you see in the JV curves is that unlike the organic photovoltaic systems where you see a loss in current, in the case of the perovskites, your current goes down, but your fill factor is absolutely destroyed due to that crack formation within the film. So ultimately, these are not the best devices for maybe flexible applications or where high flexibility is a design criteria, but certainly perovskite solar cells work really, really well. The problem with putting up a state-of-the-art slide is that it's out of date the next time you give the talk. So I apologize. There are more recent science papers than these. But just to highlight 2 different types of device, Yang Yang's work out of UCLA showing very nicely that you can make a planar heterojunction structure. If you optimize the various layers, get really good control over the perovskite crystallinity, you can make a device that's 19% efficient. Really, really impressive efficiencies. And of course, the work from SOAK in Korea on mesoporous titania, still using that mesoporous TiO2 framework. In this Nature Materials paper, he's able to get 16, 17%. Of course, more recently, those numbers have gone up. But the really nice thing about this system is that you can make mesoscopic structures, you can make planar structures. There's a variety of device architectures, lots of room to play, and you can still make them work really, really well. And so, of course, the current record, this is another slide that goes out of date very quickly, but the current record is now 20.1% out of SOAK's lab for a certified efficiency for a perovskite solar cell. And if you stack that up against things like multicrystalline silicon or cadmium telluride, I mean 20.1, 20.4, what's 0.3% between friends? So these are really efficient devices. They're very competitive with established technology. And so efficiencies are not what's holding this technology back from being commercially exploited. And so, of course, for anybody who's tried working with these cells or left them out on a bench overnight, that's the problem is obvious. But the issue is stability. And this is really the number one issue that plagues these cells. If you take a nice brown perovskite film and you expose it to a humid atmosphere over the course of maybe a day, you see your nice brown color disappears, and you see this lemon yellow, lime green color come in due to the formation of lead iodide. So your perovskite film decomposes, and it decomposes very, very rapidly. Now this is bad, of course, in terms of long-term device performance. You don't want to replace your module every day, or every week, or every month, or even every year. You want something that's going to last for 10, 20, 30 years, and we're obviously a long way away from that right now. But of course, you might be worried about the lead in the byproduct. So lead in the lead iodide, well, that's not good. That's a toxicity issue. But you think, okay, well, in the first semester of Gen Chem, I learned that lead iodide is insoluble. So that's good, because cadmium telluride is insoluble. And so people don't worry about the toxicity of cadmium so much because cadmium telluride is a brick. It's stable, it's insoluble, so the cadmium is not bioavailable. And so you might look at the lead iodide and say, well, that's insoluble, that's not going anywhere, we should be fine. But of course, I teach Chem 115, so the second semester of first year. We talk about equilibrium constants and solubility products. And if you look at the KSP of lead iodide, it's actually kind of high. It's about 10 to the minus 9, 10 to the minus 8. And if you work that out, this is actually soluble in water to the tune of 1.6 millimolar, or about 250 parts per million of lead. And so if you have a module that's out in the field that becomes damaged, your encapsulation breaks, you're now leaching 250 parts per million of lead into your groundwater, and people aren't very happy with you. So more than anything, it's really the instability of the perovskite, which gives rise to these toxicity issues, that's the biggest barrier to commercialization. So this is what we have to address. And so trying to look at that has been what's consumed our group for the last little while. What we know, of course, is that if you take a perovskite film, you have a nice band gap around 760, and you expose it to moisture, you get a yellow film. It gives you this red trace here. Looks an awful lot like PBI2, very, very similar UV vis spectra. So we have a pretty good idea of the end products. So A turns into B. But what we don't know is how fast that process happens. And there's a big difference between a foggy day in Santa Barbara and a dry day in the middle of the winter in Saskatoon, where your ambient humidity might be 10%. I get regularly shocked by touching my filing cabinet. It's really that dry. And so we need to control the environment. We need to benchmark how fast these things decompose, because if you can control or measure the rate of decomposition, you can start to do something about it. Everybody in the PV field chases efficiency because we have a number. Okay, my number is bigger than your number. This method must be better. But what we don't have is a number for how fast these things are decomposing. And so if we can start to measure that, maybe we can start to improve it. So that's what we did. We did a little bit of plumbing to put together a setup to control the relative humidity above our film. So what we did is we take a carrier gas, run it through some water-filled bubblers, create a saturated stream of water vapor, take a second stream of carrier gas, control the ratio of the two streams to control the humidity. Eventually we pass that over our sample holder, and we have an RH sensor downstream. So we can nicely control the relative humidity inside this chamber. And this is designed, of course, just to slot into our UV vis spectrometer. So we can get in situ data as our films are decomposing. So if you do that, and the data actually comes out looking pretty nice, you can see a bleach of this high energy absorption band your band gap goes away, and you actually see a big increase out here simply due to an increase in me scattering within the film as you get large crystallite formation. If you pick a wavelength where you're seeing some of the biggest changes and plot that as a function of time, you can now get a nice smooth kinetic trace for how fast these things are decomposing. And this is at about 98% relative humidity. And of course, the answer to how fast is pretty fast. After about 6 hours, there's nothing left of your perovskite film. It's been completely degraded in this humid environment. We did this in nitrogen, in air. We did it multiple times. At the end of the day, all of the data is fairly reproducible. Again, about 6 hours, everything is dead. The key point here is it's not oxygen in the air. It's really the moisture that's the fundamental issue. And so the question is, well, how much of an issue and how can we change it? If you decrease your relative humidity to 80%, your devices last a little bit longer, maybe a weekend rather than just a work day, but still decompose very, very quickly. 50%, 20%, they decompose more slowly. And so the scatter in the data is just from putting the sample in and out of our UV vis, just so we're not hogging the instrument for 1,000 hours at a time. What I think is actually really encouraging about this data, though, is at 20% relative humidity, the decomposition rate is slow. And so this suggests that maybe you don't need absolutely perfect encapsulation, that maybe encapsulation is an actual viable strategy to produce perovskite films that are stable over the long term. And so maybe it's not so much of a chemistry problem, maybe it's an engineering problem that somebody else can worry about. But what we did observe with this sample holder was actually an effect of the whole transport material. If you think about it, the whole transport material is sitting between your perovskite and the rest of the world. And so it's acting as a bit of a barrier to moisture ingress. And so if you look at something like spiroomatad, you were hoping, okay, maybe it protects the underlying perovskite. Nope, if anything, it makes things worse. Polytriarylamine, ditto, very, very little effect. But if you go to something like P3HT, there's actually a bit of an induction period before your perovskite film decomposes. And it was kind of interesting to see why that might be. And so we looked at the morphology of these samples for clues. This is what a dead perovskite film looks like. You see lots of these big hexagonal plates of lead iodide. You see these dendritic structures, and then a whole big mess of partially decomposed material. If you put a layer of spiro over top, you now have a nice skim of barrier material, but the spiroomatad is brittle. It's a small molecule. It cracks. You get these big micron-sized holes, and just allowing the moisture to bleed through. So you get very, very rapid decomposition here. Polytriarylamine is no better. You see all of these pinholes. The film looks like Swiss cheese, these big craters that are microns in size, really just allowing, again, moisture to penetrate through into the film. With P3HT, you actually get a nice conformal coating. So it's not a crusty skim of whole transport material. It actually adheres very well to the underlying topography. And so even though this film has been completely decomposed, again, you see these dendritic structures, lead iodide, it took an awful lot longer to get to this point. And we think that part of that is this densely packed, interdigitated P3HT film that's able to protect the underlying perovskite. Not a lot. This is not an encapsulant, but at least a little bit. And so it's interesting clues to how we might be able to improve device stability. Now, the one thing that we weren't able to get from UV vis is any structural information. What we know, something black turns into something yellow. That's what UV vis tells us. And so we wanted to get some structural information. This is where the synchrotron comes in very handy. We wanted to do some grazing incidence X-ray diffraction. We can be fairly sensitive to a thin film, but most importantly, the high brightness of a synchrotron X-ray source gives us lots of photons in, a fast area detector gives us the ability to collect photons very, very sensitively. And so we can get a diffraction pattern in about 1 second, so in real time. And so we can sit there and watch as our perovskite film decomposes. Now our data wasn't great on the first time out. We clipped a bit of our glass substrate, but you can still see some of the key reflections from the underlying perovskite film. So this is our setup at the hard X-ray microanalysis beamline. Beam comes in from this side. We've got a nice in situ sample chamber, humidity in, humidity out, so we can control the environment. We've got a resistive strip heater and thermocouple, so we can change the temperature. This is sealed by a Kapton window, and then we've got our area detector over here. And so what you get is some noisy looking data, but if you look carefully, you can see some reflections due to the perovskite, and then the appearance of these new features as you flood the chamber with moist air. And what happens, you can see this better in the 2D plot, is you actually get, here's your perovskite, you get this intermediate decomposition product showing up after a couple of hours. So you've got this nice feature that grows in as a function of time. And your first thought is, oh, there's our lead iodide. That's not what this is. Doesn't line up. We tried calibrating this 5 ways from Sunday. There is no way that this thing is lead iodide. Just didn't line up no matter how we squinted at it. And so this was really puzzling. We had some unknown intermediate in the decomposition pathway. And so we did one more experiment to try and nail this down, and that was to look at whether this was reversible. And it turns out that it's actually a little bit reversible. If you completely decompose your film, you have now that bright yellow substrate. You turn off the moist air, you turn on dry nitrogen, you see a regeneration of this band gap feature at 760. You don't see the whole thing come back. This is not a resurrection of your perovskite film. It's still not in good shape, but there's a little bit of this band edge that comes back again. So it's not 100% one directional. And so we were putting this into the context of what was known in the literature. And New and co-workers had proposed this decomposition mechanism earlier in the year, where it's an acid-base reaction between the methylammonium cation and water, which forms methylamine and lead iodide. Okay, well, this gives us our PBI2. Problem is that methylamine is a gas, and we're in a flow-through cell. So if we're liberating methylamine, you'd expect that to be swept away as we purge the headspace of our sample holder. And I don't know that that's really consistent with the reversibility that we see in the films. So we dug into the literature a little bit more. This is where this paper comes in from the Canadian Journal of Chemistry out of a group at Dalhousie University from 1987 when I was much younger. They structurally characterized this material on crystallizing the perovskite from an aqueous solution. And it's a methylammonium lead iodide hydrate, which actually corresponds really nicely to our mystery phase in our grazing incidence X-ray diffraction data. So it was a bit of a back to the future experiment where we actually did the data, got the data, saw the phase, and then rediscovered that somebody had done it 30 years previously. But this corresponds really well to the first step in the decomposition mechanism. So the film picks up moisture, breaks apart these lead iodide octahedra into discrete PBI6 units. You've broken apart the connectivity between the PBI6 octahedra, and now you have something that's pale yellow instead of the black color that we started with. And of course, if you dehydrate this, if you heat this sample, you can drive it back to the methylammonium lead iodide as long as your PBI2 hasn't phase separated. So it hasn't crystallized out separately. So this was a nice bit of mechanistic information that we were able to glean out of these in situ diffraction experiments. So in the last couple of minutes of my talk, I'd like to just talk about one other last stability issue that we've run into. And it's something that's a little bit unique to our group because we work so much on zinc oxide. We put all this effort demonstrating that these zinc oxide electron transport layers work really well. The problem is that they also make the perovskite film unstable, more unstable than it already was. And so if you take a perovskite film on glass, on ITO, on titanium dioxide, and on zinc oxide, you put them on a hot plate, you heat them to 100 degrees. These three are fine. This one decomposes. And so there's something about this zinc oxide electron transport layer that is unstable when it forms an interface with the perovskite. So all of these substrates, we've done PPSS, we've done any number of other different substrates. Zinc oxide is the only one that induces this decomposition. And this is at a fairly low temperature. It happens at 80 degrees if you leave it for long enough. And if you think about a module, your nominal cell operating temperature, depending on how much heat sinking you put into it, might be 50 degrees. And that's assuming an air temperature of 20 degrees, less than 1 sun insolation. And so if you move from Santa Barbara into the Mojave, where you're lucky if your air temperature is not 45 or 50 degrees, well, suddenly 80 degrees on your module is not unrealistic. And so you really have to worry about not only the moisture instability, figure, okay, you go to the desert, that should be fine. Well, now you have to worry about thermal instability as well. And so no matter which way you turn, you're running into these stability issues. And so the first thing that we thought this might be was, well, maybe the zinc oxide is hydrophilic, it's drawing moisture into the film, and that's exacerbating this problem with humidity. So we ran these films through our in situ humidity cell. And what we actually find is that the zinc oxide, if anything, makes the perovskite film a little more stable. So there's actually less decomposition on zinc oxide than there is on glass. Not by much, just a little bit, but clearly this didn't seem to be the reason that our films were decomposing. And of course, the nail in the coffin is if you do the experiment inside the glove box, where hopefully you have very, very little moisture, your film on zinc oxide decomposes, your film on glass is perfectly fine. And so this is not a moisture-induced problem. Moisture is not part of it. This is really a thermal issue. And so not knowing where else to turn and having a little bit more beam time, we popped it onto our sample holder for some grazing incidence diffraction. What we see here is, again, some nice ring features due to our perovskite film. And this one's actually fast enough to play a movie. You can watch as your perovskite disappears and your lead iodide grows in. And so it's a really smooth A to B transition. There's no intermediates. All of these line up really nicely for lead iodide. So it's perovskite PBI2. So starting material and product, and a very, very rapid decomposition process. So we're trying to understand why that might be. And what we came back to was sort of the old Sesame Street song of one of these things is not like the other. And if you look at the acid-base chemistry of silicon dioxide, titanium dioxide, tin dioxide, zinc dioxide, as defined by the isoelectric point, what you see is silicon dioxide, yeah, you've got some silanol groups, they're a little bit acidic. Titanium dioxide, a little more neutral, but still maybe on the acidic side. Tin dioxide, again, a little bit acidic. Zinc oxide on the basic side of things. So the surface chemistry is a little bit different as you go through each of these samples. If you look at the methylammonium cation, well, that has a pKa of about 10.6. So it's not a strong acid, but it's definitely a weak acid. And so the idea that the zinc oxide might be basic enough to deprotonate the methylammonium cation is not entirely unreasonable. And certainly in this case, your byproducts become HI, PBI2, and methylamine. This can drift away. The HI may then eat away at your zinc oxide layer, liberating water, which attacks your perovskite further, and the whole thing falls apart. And so this, we think, was really the mechanism by which these samples decomposed. Now, at this point, I presented this work last November and had a really interesting conversation with Filippo D'Angeli, an Italian theoretician. He was sitting on the couch. I was sitting next to him. He leans over and says, "Oh, I'm really sorry. I missed your talk. I had to go to a meeting. What were you doing?" "Oh, well, we did these stability studies. We saw it. We think there's some deprotonation of the methyl ammonium from the zinc oxide surface." "Oh, yeah, we ran those DFT calculations, and we saw proton transfer from the methyl ammonium cation to the zinc oxide surface. I'll email my postdoc right now and get the data." And so 20 minutes later, before dinner, we had the DFT calculations done and some nice theoretical evidence that this was actually the case, that the zinc oxide was able to deprotonate the methyl ammonium cation at this interface. And none of this was observed on TiO2 or any other substrate. This was unique to the zinc oxide surface. So it was a very productive 5 minutes on the couch, very nice walk. So that paper is now in submission. The interesting thing that we went a little bit further, it's not just that the zinc oxide is actually more basic. That's part of it. But there's also the residual surface chemistry of the zinc oxide. So these are made from a low temperature solution phase processing method. So we have hydroxyl groups, we've got residual acetate ligands, and of course if you thought zinc oxide was a problem, well, acetate is a base, that's a problem. And so that actually exacerbates this issue. So if you thermally anneal the zinc oxide films at 100, 200, 300, or 400 degrees, you can eliminate, calcine away these hydroxyls or residual acetate groups, and it actually makes the films a little bit more stable. So showing here from left to right and top to bottom, the pre-annealed zinc oxide surfaces, and then this one's just on glass. Heat them to 100 degrees. These ones, which are the low temperature annealing, decompose first, followed by these next two, so the higher temperature annealing. This guy holds on as long as it can, but after about 80 minutes, this starts to decompose, and the sample on glass is still nice and brown and shiny. So really, even though you've eliminated all or most of the acetate or surface hydroxyls, you still get decomposition on the zinc oxide surface. And so clearly, this is not the most ideal electron transport layer for this material. So just to sum up some of the main points here, perovskite solar cells absolutely work well. They give you very, very good power conversion efficiencies. It's been really marvelous and gratifying and wonderful to look at the just steady march of record-setting efficiencies. But the problem is that they're not stable to moisture, and depending on your electron transport layer, not stable to heat. And so we need to somehow address that. And the first step to that is figuring out why they decompose, how they decompose, and how we might be able to prevent that. So we've been doing a lot of in situ spectroscopy, some environmental controls to try and get a handle on that. But as far as the big take-home message, the key is that you need to view not just a number, a power conversion efficiency, and take that as your guiding star. You actually need to take a more holistic approach and consider various components, not just for their performance, but also for their effect on stability, for their effect on the processing techniques that you can use. It really comes down to the applications and the particular design criteria that you want to use. So finally, I just need to, of course, thank you for your attention, but also thank the people who did the work and paid the bills. So this was the group at Christmas time. In particular, I'll point out Dr. Diani Liu, who really got us started in the field of perovskites. Kinush, who did a lot of the flexible devices. Dr. Jin Li Yang, who took the lead on all of the in situ spectroscopy and diffraction experiments. Mahesh has contributed quite a bit as well. In particular, I'll point out Braden Simpelkamp. He was a summer exchange student, second year undergraduate biochemist who had maybe first year Gen Chem under his belt when he joined the group. And between he and Jinli did all of the in situ spectroscopy, in situ diffraction, start to finish. Really, really talented individual. So finally, thanks again, Quinn, for the invitation to come here, all of you for your attention. This is the chemistry building. This is what I am not in right now. So thanks again for that.
Tim will be happy to answer any questions. Any question from the audience?
I have two questions. First, is it possible to dope these perovskites? So finally, is it possible to prepare PN junction based on perovskites since it's inorganic material? And second question regarding the instability caused by zinc oxide layer. So maybe is the issue from the way how you prepare it, not directly from zinc oxide. Did you try to check this instability with the zinc oxide deposited by magnetron sputtering, so without any residual chemicals?
So for the first question, I guess, so the issue of doping, I mean, it's not really electronic doping in the same way, but if you do substitutional doping, put in bromides for replacement for iodides, of course, you can tune the band gap. You can do all sorts of nice chemistry that way. In terms of the PN junction idea, people like playing with tin because it's not lead, and they say, okay, well, we have tin, now we have tin 2 and tin 4, and you can imagine really controlling the doping levels, except they almost always overdope, and so you end up with so much tin 4, the whole thing shorts, and everything falls apart. So most of the work has been this PIN, whole transporter, perovskite, electron transporter structure. Second question about the magnetron sputtering. That would be really neat if we had a magnetron sputterer. So we're limited a little bit by the available equipment. We don't happen to have one on campus, at least not one that somebody's going to let us use. If you have one, that would be interesting.
Yeah, I just had a question for your stability. Has anyone looked at the difference in stability when it's under operating conditions, like illuminated versus just sitting around?
Yes. Filippo, I know, has even done some simple experiments where he somehow plumbed in a solar simulator into the diffractometer. The whole thing falls apart. So I don't think light makes them any better. I don't know how much worse it makes them. I don't think it was a very quantitative study, but nothing is good, I think is the take-home message.
So have you tested because you test in ambient condition, have anybody tested it by lifetime under encapsulation to see it lasts?
Some of Gratzel's devices, so he's got a nice setup for light soaking experiments, encapsulated 500 hours, looked pretty good with actually very little loss in efficiency. I'm a little bit curious how much that changes between a planar structure and a mesoscopic one. All of the mesoscopic devices seem to have no trouble getting certified. That's more of an issue for stable enough to get there. Yang Yang talked about his science paper, and you're not far from Newport here, and even he had trouble getting his devices to survive that long, just for the trip through LA. Which.
Any other questions, Jack?
You showed the different thicknesses of the devices. The thinnest one didn't work very well. I realized that it didn't absorb light, but also had very low pull factor.
So probably the easiest thing to do is look at a picture. So if you look at the SEM images of our films, this is for something that's maybe 300 nanometers thick. We've got a really polycrystalline morphology, lots of grain boundaries, lots of little gaps. And if you can imagine this being now a film that's 100 nanometers thick or 150, if you get contact through these gaps, you end up with more recombination that way, simply by micro shorts across or through the device. So I think that contributes a lot to the loss of fill factor at the very low or very thin thicknesses. You can't prevent your two electrodes from coming into contact. If we had maybe a nicer, better control over the quality of our film, that might be less of an issue.
So to follow up with that question, because based on what we reported in this material, that the electron hole mobility is quite high, right? So I would expect that for the thicker film, you should be able to make very thick film because you don't limit by the mobility by extraction. But what you show that also thicker film, you have the issue with extraction. And I would assume that for that case, the main drop in the PCE is due to the lower fill factor and also lower short circuit current.
So I think it comes back to morphology.
Right.
Because we would like to put a label on this material and say, okay, it has a carrier diffusion length of 100 nanometers or 1,000 nanometers or 175 microns. The initial studies that were done, the back-to-back science papers by Gratzel and Snaith, reported carrier diffusion lengths for this material of 100 nanometers. And so for a 300 nanometer thick film, yeah, you're pretty much just at the cusp of exceeding those diffusion lengths. So you're starting to get losses due to recombination. It depends, I think, of course, on the crystal quality. If you have a single crystal of this material, then sure, those charges can go a long way. But I think the grain boundaries are really impeding the carrier transport, which is why there's always this debate over, does chloride do anything? Is it still there afterwards? And so when Snaith reported the 1,000 nanometer carrier diffusion length, at least my own take on that is that it's simply a more crystalline film. It's not that the carrier diffusion length in the material is any better, but the film crystallinity is so much better with that little bit of chloride in the mixture that he reported then a much longer.
So I had a quick question on the zinc oxide kind of taking the hydrogen. So I'm not sure if I didn't catch it, but you showed a kind of ball and stick diagram. It seemed that you had kind of an ideal interface between the zinc oxide and the perovskite. And it would seem to me that interface would be, or the surface of zinc oxide would be already hydrogenated before, from step one. So, did you kind of take that into account, or does that just change the barriers a little bit?
So the theoretical work was all, single crystal, theoretically slice, put it onto a zinc oxide surface. So it's a very idealistic picture. I think what it does give us is a suggestion that thermodynamically, the idea is not crazy, that you do have enough basicity there to potentially pick off a proton. Of course, with our synthesis, we do this from potassium hydroxide solution in the presence of acetate. And although we wash it with methanol, we never really reacidify the surface. And so I don't know that we really have a fully over-protonated surface, if you will. I don't think that's so much of an issue. So I think it's still certainly possible that we're plucking off those protons from the methyl ammonium cation.
Yeah, so in using the nanoparticles, the zinc oxide nanoparticles instead of a mesoporous material, there's a huge difference in surface area between those two. Is that going to have a really significant effect on the efficiency of your material?
Potentially. So it comes down to the crystallinity and the quality of the film that you put on top of it. In the case of the mesoscopic device, you don't necessarily need a long charge carrier diffusion length because it can be sucked up by the TiO2 extraction layer. In our case, we do because the perovskite is carrying those charges in both directions. And so if the film gets thicker, then we see a decrease in efficiency. Similar studies on mesoscopic supports have sort of revealed optimized film thicknesses of closer to 400 to 600 nanometers. And so you can make the film a little thicker because you've got that high surface area electron selective contact. So you can more effectively extract out your carriers. But in theory, as with Yang-Yang's work or some of the recent, one of the recent papers from Los Alamos in Science, if you have a really good crystal, your charge carrier diffusion lengths are really, really long, and it hardly matters how thick you make that layer.
So if no further questions, let's thank the team again for a wonderful lecture.
Thanks again.